e-learning sessions. Thank you again for joining us. This week we're thrilled to have Rockwool joining us for corrosion under insulation discussion. And what we quickly found out was this problem does not discriminate. It's actually a global problem, and you can tell by all the people that have joined us from provinces and countries around the globe. Alberta, Ontario, Nova Scotia, Scotland, Turkey, Indonesia, and yes, another mystery country right here. If you can guess that country, go ahead and text it, and Dan Morgan will be announcing any winners. So we'll give away a free hat to the first 3 winners and guess that country. And if you're wondering why you're taking one last look at that country, the furthest distance, if my algorithms are correct, between any 2 points today are in visitors is between Charlotte, North Carolina and Jakarta, Indonesia. So Peerless, we've been around for over 100 years. That is our old building, downtown Buffalo. For years, we operated out of a 5-story building. About 3.5 years ago, we moved into the building on the lower right-hand corner, where it's much more efficient for us. We can operate far more leanly. So we have become known as a relied upon distributor and manufacturer for process components. We operate out of 3 segments: our high temp fabrication group, where we do work with high temp insulation, pipe and valve insulation, refractory, and lab surfaces. Our process group, we do work on a lot of MRO for the chemical pharmaceutical type of industries, and the OEM group, where we work on a lot of very high spec projects that end up global. So today we have Dave Adamski with us. He is the specifications sales manager for North America for Rockwool. Dave, thanks for joining us. We also have Jonathan Osei-Kaffour. He is the regional marketing leader. On the Peerless side, you see some familiar faces. It's Dan Morgan, there's Greg Barrell, and of course, me. So I asked Dave a little bit about himself, and quickly he said that he is a golfer, and he famously was involved in the Wayne Gretzky and Friends Invitational up in Nova Scotia. And when I asked him further, I asked him who he golfed with, and it was Mike Weir, Wayne Gretzky, and Brett Hull, and Mario Lemieux, but I had a hard time finding an image of all 5 of them. I kept looking and did find it, but strangely 5 people can't golf. So when I pressed him a little more, he said, actually, I was the scorekeeper, not a golfer. And a little bit more, I learned that he spent more time listening in on their conversation than anything else. So Dave, thank you for joining us. Thanks for that story. And speaking of listening in on conversations, you're going to want to hear what Dan has to say about the web platform, the meeting platform today. Dan?
Yes, thank you, Kevin. And thank you again to everybody joining us today. I'm just going to explain a couple of things here, how this is going to work and what you're seeing in the control panel in front of you. So in just a minute, I'm going to turn the presentation over to Dave, and he's going to get going with his presentation. But if at any point during the presentation he stops on a slide and you have some questions or want some clarification on it, we're encouraging you to ask a question, any questions that you have throughout the presentation using the questions panel in your control screen here. So type out a question, send it in. I'll be monitoring that and finding appropriate times to interject into Dave's presentation to make sure we get those questions answered for you. Additionally, once Dave's done with the presentation, we'll do a live question and answer at the end, where how that will work is you can raise your hand, which is another button you see in your control panel, and I'll be unmuting you essentially one by one, so you can audibly ask your question of Dave, and we can have a little interaction that way. So, and again, to Kevin's point about the mystery country, if you have an answer to that, you can submit your response through the questions panel or the chat panel, whichever one works for you. And yeah, one more thing to mention, you'll also see in the panel a handouts area. And in that area, there is a link to a PDF to what Rockwool calls their process manual, which is a very in-depth, thorough, technical guide for all things insulation for industrial applications. So please do give that a look. It's a great resource. So with that said, I'm going to turn it over to Dave right now.
All right, I trust that all can see my screen. And to kick this presentation off, I'm going to introduce to you Jonathan, who is going to give you a brief overview of who Rockwool is and how we function with all our clients. Jonathan, you ready?
Yeah, I'm ready. I'm ready. Thanks for the introduction, Kevin, Dan, and Dave. And thanks to all of you guys for joining us today for this webcast session. Today to just really discuss corrosion under insulation and its impact. But we have a lot to cover today, so I'll keep this brief so my colleague Dave can get into the meat of this presentation. So during this presentation, we hope to keep you all engaged, so feel free to ask questions like Dan said, if you have one. Starting off with this slide, and thanks, Dave, if you can keep scrolling for me, we'll stay on this. At a high level, Rockwool, as we are named today, wasn't always the case here in North America. We've transitioned from this name from Rockwool in 2018 to align and bring cohesiveness with our global company in Denmark, the Rockwool Group. A bit of informational points regarding the Rockwool Group is that we employ a little over 11,000 people globally, and we have 40 factories globally as well that serves 5 different brands across multiple industries, all using the power of stone as the critical raw material. The company started in the 1930s in Denmark, which is still the home of our headquarters today. If you can go back to the slide before regarding North America right here. In North America specifically, we have 6 factories. Our newest one is being constructed in Ranson, West Virginia, and is set to be online in 2021. Grand Forks is the factory where we produce most of our Mandra wound pipe sections with WR Tech, in which Dave will cover a little bit more in his presentation today. Going to the next slide. So Rockwool Technical Insulation. We joined the Rockwool Group in 2004 to focus a little bit more on the industrial side of the business. So we're a bit smaller, but a focus segment that focus on the business of process and marine and offshore. If you go to the next slide, just want to talk a little bit about why I choose Rockwool. We like to showcase this slide specifically to just show the landscape of our customers that we work with, from global owners to global engineering, procurement, and construction companies. So we've worked with pretty much everyone. We're a tried and true company, and we've been here for a while and have a proven track record. And the last thing I just wanted to show you guys was just our overall segmentation and what industry segments that we work within. So if you look at this chart, this infographic that was created, it's really great because it shows all the different segments that the power of stone can influence, whether it's the offshore exploration, drilling, and production side, which is also upstream oil and gas, to traditional upstream land oil and gas drilling and production operations. We do a lot in SAGD, which is in the Canada, Western Canada market there. Downstream oil and gas, which would be your traditional petrochemical plant, processing plant of that sort. Then we have the power generation side as well, where we deal with a lot of high temperature insulation components there, and down to consumption, manufacturing, and then obviously marine, which are Sea-Rock's product. But again, we wanted to power through that just so we can get to the meat of this conversation. So without further ado, I'll pass it over to the man you guys came here today, and that's Dave Adamski. So go ahead, Dave, you can take it over.
Thank you, Jonathan. And Peerless, thank you for welcoming us to be a part of your eLearning platform. As introduced, I'm Dave Adamski, the North American Specification Sales Manager for Rockwool Technical Insulation. We appreciate everyone taking the time out of their day to tune into this webinar. Today's presentation is about reducing total cost of ownership with a focus on CUI, as it can be a big part of maintenance budgets. First, we'll talk briefly about why insulate at all. Then we'll go over CUI, or corrosion under insulation, but forevermore you'll know it as CUI, and some methods on controlling this form of corrosion. We'll review what to look for in choosing an insulation. Also, we'll look at some tools outside of the insulation that can help manage water ingress and egress. Finally, we'll wrap up with some valuable resources you may not be familiar with for developing your own maintenance and inspection programs. So, total cost of ownership. When we talk about total cost of ownership, the expenditures can be grouped into 2 main categories, CapEx and OpEx. CapEx being capital expenditures and OpEx being operational expenditures. Most owners are well aware of the CapEx costs associated with design and installation. However, with OpEx, or OpEx I should say, costs are more complex and they're just oftentimes harder to decipher. We have energy utilization, impact on production rates, there's carbon dioxide emissions people have to worry about now, waste, and then of course, corrosion under insulation. We've been hearing from a lot of owners that a big portion of maintenance budget is dedicated to CUI. It can represent up to 40% of their costs. So we recognize that CUI is a large piece of the total cost of ownership puzzle, and this is why we want to focus on unpacking what is CUI and some ways of methods that are currently being used to deal with corrosion. Our aim is to shed and offer some light and suggestions on what owners can do in the design and installation phase that will hopefully reduce some of those maintenance costs down the road. Before we get into it though, let's look at why insulation is necessary in the first place. Most owners and engineers are well aware, but since the audience is at a wide and at different levels of understanding, I just wanted to answer the easy question first. Why do we insulate? So why not just simply get rid of insulation if you're having a corrosion under insulation problem? We'll look at a few ways to answer this in the next few slides. But the first way I'd like to answer this would be to look at an example. Let's look at refineries in Europe. Approximately 5 to 10% are either poorly insulated or not insulated at all, which results in heat losses corresponding to, this is a lot, 150,000 barrels of oil per day. And if we just take a cost of even $40 per barrel, that translates into $2.2 billion a year of loss. These losses could be prevented with a simple investment of $600 million. And you know what? That gives you a payback period of less than 3.5 months. So with an investment of $600 million, you can save $2.2 billion. That's a pretty serious return on investment. So again, why insulate? Because it simply pays to insulate. The savings are hard to ignore. In the next slide, we have an interesting case study of where an owner chose to remove the insulation, but it didn't turn out the way they had planned. So here's the situation. Removing insulation to mitigate corrosion under insulation is not the way to go. So we have a storage tank. Okay, so they removed the insulation, then they coated it with an insulative paint, 7 layers. Total thickness, approximately 3.5 millimeters thick, which sorry about that, that's about 1/4 inch. Tank diameter is 12.5 meters, height is 16.5 meters. The heat loss from the tank wall, and it's tank wall only, so we're not even factoring in the heat loss from the roof. And then in using the 80% filling degree, tanks filled to about approximately 80% of their capacity for expansion, we end up with kilowatt hours of 330. The annual heat loss, well, you run the plant for 6,000 hours, you're at 2 million kilowatt hours. At a 0.06, well, this is in euros, you're dealing with 120,000 euros per year of loss. This is what's going on because of the cost of heat. Well, if we insulate, even if we put 2 inches or 50, it's 96,000 euros, or 8% of the 120,000 euros per year. The installation cost of that is approximately 37,000 euros. Or if you go to the other extreme, you go to 150 millimeters, approximately 6 inches. The installed costs are 112,000 euros. Or sorry, the savings are 112,000 euros with an installation cost of 52,000. So again, as we said earlier in the earlier slide, it pays to insulate. It saves us considerable money in our facilities. The case study demonstrates how a simple solution such as insulation can have a dramatic effect on the cost of ownership. Here are some other reasons why owners come to us. They ask us to help them with issues related to course, cost of heating, process control, frost protection, CO2 emissions. Then there's safety. We got fire protection, we got personnel protection, and then acoustics related to noise control. Insulation checks off all these boxes. It's quite versatile and can fit so many ways of helping control the cost of ownership. So our topic is corrosion under insulation, and as said, you will now always know this term CUI. Insulation has a lot to offer, but with that comes specific challenges, namely CUI. In this next section, we'll go through some stats and some facts about corrosion. A study done by Exxon estimated that 83% of CUI incidents happen on pipelines. Aging facilities are affected by erosion, corrosion, and fatigue. Up to 50% of the safety hazards are caused by pipe leakages or ruptures. Damaged insulation not only poses a risk for CUI as it's a source for water intrusion, well, the heat losses can lead to major loss in efficiency and money. You may be already aware of this stat, but NACE did a study in 2016 that pegs the global cost of corrosion to $2.5 trillion per year. So what exactly is CUI? Well, if I could be really simple about it, I'd just tell you it's rust. It's caused when water intrudes into the system and gets trapped between the insulation and the unprotected surface of the pipe. Rust is an oversimplification because, but for visual purposes, if you can understand rust on a metal surface, you're on your way to understanding corrosion under insulation. And of course, water and moisture come from a variety of sources, whether it be rain, condensation, just washdowns, maybe you're cleaning up the area, and then of course, just simple leaks or spills in the process. CUI has a range where there's high risk. The slide in front of you here sort of demonstrates the various ranges of temperature of your process where CUI is low to extreme. And of course, you notice quickly that the extreme temperature is on a cycling system that cycles between, say, -20 Celsius up to 320 degrees Celsius, also known as -4 to 608 Fahrenheit. But the high risk zone that is more common in many of our facilities is from 122 to 347 F. And of course, accelerated risk areas are any facilities that happen to be near coastal areas because salt water helps accelerate the corrosion, or high humidity areas. And of course, as mentioned, if you happen to have a cycling facility, that puts us into a new extreme as far as what we need to concern ourselves with corrosion under insulation. So CUI is a challenge for sure. There's many factors involved. You got to consider the surrounding environment for sure, not to mention just what is my plant actually doing. There's the equipment and the system design. Then of course, choice and installation of the coatings that you would maybe put on the surfaces of your pipes, definitely the insulation. And then as a protective area, you got jacketing and cladding to consider. Then finally, you really got to look at the fact of inspection and maintenance so that you can spot where some vulnerabilities may be. Costly problem is, due to more frequent repairs. So when you're looking at CUI and you're looking at your maintenance budget, these things all contribute quickly, very quickly to the cost of the maintenance of the plant. And then when it comes to your safety program, CUI, when we talked about ruptures and spills, of course, that can add to personnel problems where people can get hurt quickly. It can put you at risk of fire, and not to mention just simply pollute the surrounding environment. With the equipment design features, with a lot of engineering here, we can do things that can help physically manage for reducing CUI. So of course, in you're doing your equipment designs, we look for things such as areas where water can be trapped, or make sure we have smooth surfaces for water to quickly shed. And then, of course, you design your systems so that we can literally prevent water getting into the system at all. Material selection and installation. Properly designed and installed jacketing, cladding system, that's your first line of defense. Use of suitable coatings on the system for pipe surface protection. And we will get further into these as this presentation goes on. So if any questions are starting to rise in your head, I'm hopefully going to address them as we proceed here. And then, of course, choosing an insulation material is very important. It has to have corrosion reduction characteristics. And like most facilities or any process situation, quality control is paramount to ensuring that all things are working together to prevent the single problem you're trying to prevent, and in this case, it's corrosion under insulation. So QA programs will help monitor the whole process. Then throughout the QA process, you can come up with an inspection and test plans, and then just proper equipment care so that with inspection and test plans, you can come up with prompt and effective maintenance. You can assess risk-based inspection procedures, and then with proper safety protocols in place for care of equipment, you avoid the foot traffic and any other unnecessary activities that may damage the system. So then you got choice of coating. Now, this particular chart you see in front of you references the NACE SP0198 2016. And when I speak of coatings, I'm talking about an actual coating that goes on the surface of the pipe steel or tank, as you see in the pictures, that allows for protection against sitting moisture on the surface. This puts a barrier between sitting moisture and the actual metallic surface. So NACE has outlined specific procedures for dealing with surfaces at various temperatures to help mitigate the corrosion situation that we often face in these facilities. So of course, when your coating system should be suitable for the operational temperatures, so you got to check your coatings. Surface preparation is critical. And then of course, once it's all coated, you do have to avoid damage of the coating after application. So all these things can be factored into an inspection and test plan in relation to controlling CUI. So what about the insulation material? Rockwool has done a lot of research based on what NACE says in their CUI guide, and I'll do my best to give you a high-level summary of our findings. The full findings for this are available in white papers on the NACE website. So the insulation material. As a major insulation manufacturer, Rockwool, we recognize that we have a role to play in the CUI issue, and we're in a unique position to help solve the problem. It's an industry problem because CUI is not unique to stone wool. Corrosion under insulation of carbon and stainless steel is possible under all types of insulation. The most influential characters of insulation are water repellency, permeability, as well as water leachable salts, such as chlorides or sulfates, and other acidic elements that can accelerate corrosion. This is best summed up in a statement within NACE's SP0198 guide on CUI. And it reads, because CUI is a product of wet metal exposure during the insulation system, I'll start that again. Because CUI is a product of wet metal exposure duration, the insulation system that holds the least amount of water and dries most quickly should result in the least amount of corrosion damage to the equipment. So what NACE is basically saying here is reduce time of wetness and you should reduce corrosion. Rockwool went about trying to test out this NACE statement by performing a couple of standardized tests. The first test we looked at was investigating dry out times and their relation to corrosion. We used the ASTM G189 test, which is the standard guide for laboratory simulation of CUI, and this test uses a heated stainless steel pipe with insulation and full cladding. As you can see in the photos on the bottom right, this test injects water through the cladding and insulation right to the pipe surface, and this simulates like a hole or a crack within the insulation system. The test rig is exposed to a wet and dry cycle. You get 20 hours of wet, and then we allow for a 4-hour dry. We did this for 21 days to find out what would happen. And so here are some of our key findings as we look at these images of corrosion on the top and bottom sides of the pipe. The insulations that leached out higher levels of chloride and sulfite resulted in more corrosion. Larger areas of corrosions are found under closed cell insulations versus open celled insulations. That'd be a good question for someone if you don't know the difference between closed cell and open cell. This directly corresponds to NACE's statement on drying out the fastest. With closed cell materials like PIR and cellular glass, water had a hard time escaping, whereas open cell material allowed for that vapor to escape from the pipe surface through the insulation, thus lowering the time of wetness. So corrosion result, yes.
Sorry to interrupt, this is Dan. We did actually just get someone ask the question to maybe elaborate more on what you just mentioned about the differences between closed and open cells. So could you maybe spend a couple of seconds and elaborate on that?
Yeah, that actually works well with this next slide. So here we go with that.
All right.
Okay, thank you so much for that question. So here are the actual corrosion number results. Now I do want to make a note of this. The insulations you see listed across the top are generic styles of insulation. These results are factored in for the specific generic type of insulation that was tested. These are not results specific to a manufacturer of that type of insulation. And that's important to note because not all manufacturers make the same insulation the same way. And like as you'll see, we would tell you from Rockwool that not all stone wools are alike. So it's important to note that. But to answer the question about closed versus open, that's what I really want to draw your attention to with the phenomenon as to whether closed cell versus an open cell process. Now, a closed cell insulation is simply what it implies is that it is closed. It's in itself could almost be considered a vapor barrier, because the composition of the insulation itself does not allow for vapor transmission, at least not easily. I'd never tell you that a rubber insulation or a cellular glass or a PIR is a perfect vapor barrier. But because it in its nature is closed cell, that the cell is solid, it's made up principally on the fact that it's bubbles, I think would be the easiest way to think about that. A bunch of bubbles locked together in a solid form so as to prevent the transmission of heat energy, because of course trapped air is a great insulator and it's trapped within a closed cell. But with that comes the fact that water vapor does not readily or easily pass through it, and in that event can actually hold sitting water at the pipe significantly longer or simply never let it out. And that could be a problem. Now, when you think of open cell or even semi-open cell, you've got insulation that is literally not bubbles of air. It has pockets of air, but of course these pockets theoretically leak and are breachable by vapor. And that's an important thing to note, because oftentimes when water gets into a system, and it's a hot system. That water will hit the hot surface of the pipe and basically vaporize. It'll boil, vaporize. Now, where does that vapor get to go? In a closed cell, it's still trapped inside the closed cell. But with an open cell insulation, it can permeate the insulation, get through to the other side, because the water vapors will migrate to the lower pressure side of the insulation and then find its way out of the system. And this goes to NACE's comment where it just basically says the least amount of water in and the fastest way for the water to get out will help mitigate the corrosion. Hopefully that gives you some indication of understanding closed cell versus open cell insulation. But again, not all stone wools are created equal, and I will gladly tell you not all aerogels are created equal, not all fiberglasses are created equal. But the testimony in the test is simply a consistency of corrosion problems between open and closed cell insulations. Also, at high depth of pitting can result for semi and closed cell materials. This test and these results are detailed in a white paper that we presented back in 2017, which is known as paper number 8877, titled Cyclic CUI Testing of Insulating Materials for those of you who may be interested in digging into this further. For NACE members, this paper is available and free to download. So for the person who answered that question, if I was not clear, please ask it again so that I can review it one more time. So what tests? Corrosion is directly related to the time of wetness. Less water and faster dry out equal less corrosion. The ASTM G189 testing and results presented in the previous slides looked at the drying out time part of the equation. The other part of the equation we wanted to investigate was the time of wetness, and we used the EN 13472 test and the ASTM C1763 test. The EN 13472 test is a partial submersion test. So in the lower left-hand corner of this slide, you'll see a pipe section sitting in a bath of distilled water, and it's weighted down with a bottle at the core there. So this is partially submerging the insulation in water. The ASTM test is similar, but it's actually designed for flat specimens. So that's fundamentally the difference between the two tests. The EN standard is specifically designed for pipe-shaped insulation, whereas the ASTM standard is designed for flat insulation. And in the ASTM standard, we submerged it to a depth of about 1 inch for 2 hours, and we measured the water absorption at a recovery time of 2 hours and 48 hours after wetting. So we wanted to see how fast it took the insulation to recover. These are the results from the full submersion test, and it details the water absorption characteristics of stone wool with 2 different types of water repellent additives in comparison to some other types of insulation out there. The absorption is measured in percent volume in this graph. Each bar corresponds to the amount of water absorbed and the recovery time. The insulations that absorbs the least amount of water also recover faster because there is less water to dissipate. You may be wondering how this test is different from the previous G189 test. Well, this test only looks at water absorption into the materials, whereas the G189 test looked at water escaping. So that's, again, back to the closed cell versus open cell. With the G189, we can see how fast water could escape through the different cellular structures of the insulation. And as I mentioned earlier, not all stone wools are created equal. As a stone wool treated with mineral oil, as you can see right here, stone wool with mineral oil, did not perform well as stone wool with inorganic resin. And just so you understand, mineral wool with oil or mineral wool with inorganic resin, the reason there's an inorganic resin or a stone wool with a mineral, I get tongue twisted on it because there's too many minerals in that statement, is there just a different form of a different additive into the manufacturing process that allows stone wool to resist water intrusion. So inorganic resin results in a better situation than the stone wool with mineral oil. And you will see that in other situations as we proceed forward. So once again, another key aspect of keeping water out is the thermal durability of your water repellent treatment. So again, inorganic resin versus mineral oil are called water repellent treatments. This graph details results of stone wool and other insulation materials before and after heat treatment. And by heat treatment, we simply mean the insulation was put into service and actually had to perform thermally at a temperature, and we wanted to see what was the result of the added water repellent treatment. And we did this treatment to 250 degrees Celsius for 24 hours. The reason for that is we're really interested in how the material performs in application where the CUI risk is high. And remembering from the earlier slides, that's the zone between 50 and 175 degrees Celsius. For this comparison, we use the EN 13472 test, which is partial submersion, which is a partial submersion test of our insulation for 24 hours. That's meant to simulate short-term water exposure like a rain event, and water absorption is measured in the weight of water per submerged area, kilograms per meter squared. And as you can see, stone wool treated with inorganic resin, right here, pardon me, I just choked there. Resin performed well with less than 0.2 kilograms per meter squared before and after heat treatment, similar to perlite, which also had low amount of water absorbed. But as you will notice, stone wool treated with mineral oil did not perform so well after heat treatment. So this is stone wool with mineral oil, but when it was put into service and heated up, it began to hold the water. Calcium silicate, not so great in water absorption before or after a heat treatment test. We do have a paper that goes deeper into this subject, which I would encourage our viewers to look up, and that's paper number 10929, titled Mineral Wool and Water Repellency. And as a little bonus feature, we can look at, because we often get this question, are these additives actually safe for coatings and in applications like paint shops where coatings are critical? Insulation materials and the additives that are part of the insulation can affect coating operations. We conducted a series of tests in accordance to the VW or Volkswagen paint test, whereby additives are leached out of the insulation by a solvent and captured onto a piece of copy foil. These foil samples are then coated with varnish to test for a negative effect. On the right are the pictures of stone wool with different additive types being tested. The mineral oil caused poor paint adherence. With the silicone oil, you'll notice some fisheye effects as well as poor paint adherence. With inorganic resins, there are no visible defects even when zoomed in. If you happen to notice a difference of the one slide of color, that's just based on the camera lighting as we zoomed in, just in case that was a question that may come up. So we are confident that inorganic resins were indeed safe for coatings.
Hey, Dave.
Yes, sir.
Dan again. We got a couple of questions here that came in about that testing that you just outlined in the last couple of slides. So first one, if you agree, now is a good time. First question here is, you're talking about the water repellent additives and how they perform. I believe you took it up to 250 degrees C. So do you have data on what happens to those repellents at temperatures above 250 C? And then what sort of rates that you might see at those temperatures?
Do we have data on that? I need to verify that for sure that we actually have the data, because our data and our tests were simply in the range of the highest situation of corrosion under insulation. So at 250 C, which off the top of my head, I believe is around 480 degrees Fahrenheit, that starts to take us out of the high risk area of corrosion under insulation and brings us into a whole other process situation of high temp insulation. So our inorganic resin does have an upper end limit before heat eventually can cause it to be ineffective. But at which point, then we start to talk about a whole other mitigation process for controlling water ingress and water egress. So to answer that question, if the question is, does the inorganic resin have an upper limit? Yes. Do we have data that shows what happens after the fact? I would need to verify what data we do have available, because I'm not entirely sure we went through the process of what happens to water at high temperatures in relation to insulation. So that I would have to get back to us on for sure. But as I say, when you're talking about those types of temperature ranges, we're kind of starting to cross out of the problem of corrosion under insulation. Now, don't get me wrong. I fully understand that if water gets in a system, even at high temperatures, we could get corrosion. But again, there's a different mitigation process involved in dealing with that. Was there a second question, or was that both of them?
No, that was it. And I think you did answer the question. It was, I believe the intent was about the, you know, at what point, I guess, does it become ineffective or deteriorate? So the other question is potentially a quick one here is, why was the EN test chosen, I guess, instead of not a North American or ASTM test?
Okay, the EN test was chosen specifically because it is the only test that's designed to test a shape of a pipe. So insulation formed in the, what do you say, cylindrical form, the round form, that's what the test is designed to actually test for, insulation in that form, whereas the equivalent ASTM test is for flat surfaces only. So we did them both for a direct comparison of our performance as a pipe insulation and also as a flat insulation. Does that make sense?
Yes, it makes sense. Oh, go ahead, Jonathan.
Yeah, just to add to that, the EN standard is a lot more stringent of a standard as well. It has a pass or fail criteria. The ASTM standard just measures water flow. So we like to test ourselves to the highest standard. And in Europe, they actually put corrosion under insulation a lot sooner. So that's why we take into account theirs as a more stringent standard that a lot of global OEM companies and owners are using today for their petrochemical.
Okay. Yeah, Dave, I think that answers the questions. I'll let you know if there's any follow-up to either of those.
Okay, great. No, great. The discussion is perfect. This is the type of interaction we like to have. So the takeaways are, okay, so what are our takeaways? Our takeaways are to look for low leachable chloride content, heat-resistant water repellency with an inorganic resin for low water absorption, and open for water vapor diffusion to allow for fast dryout times, and make sure the material is safe for coatings. A lot of the same CUI preventative characteristics translates to your total cost of reduction, translates to the total cost reduction characteristics. The ease of installation has an effect on CUI in terms of proper installation. So when we're looking at selection of insulation materials, if it's easy to install, there's a much higher probability of doing things properly. This is true also for maintenance, as sometimes removal and retrofitting insulation is necessary. High durability in an insulation is also important to look for in order to ensure material will last. In terms of thermal stability, water repellence, and mechanical robustness. So a durable insulation is vital. Not all insulations or stone walls are created equals, so please do your homework. Ask your manufacturers how their company is dealing with the issues of CUI. So now that we looked inside stone wall insulation and what to look for, in this next section, we'll take you through the insulation system as a whole and describe some additional accessories to consider to help manage water ingress and egress. So outside of the insulation process, you're basically going to be dealing with water that comes from the outside via leaks or leaking into the system, or you're going to be dealing with condensation. Cladding is your first line of defense. Cladding is simply the exterior jacketing put in place for the protection of the insulation and the underlying system. Jacketing or cladding has its own selection criteria, say from aluminum to stainless to galvanized, and that's a whole other presentation. And of course, you have your design. Piping systems have vulnerable points for water intrusion, supports, hangers, and joints. So it's important that you consider these things when you're thinking about water ingress into your system. Is something going to penetrate to the pipe, such as a pipe hanger? Or are we going to be running over a surface such as a pipe support? Do we got to make sure? And then of course, if you know water is going to be coming into the system at some point, you can put drain holes to be installed so that at the lowest points, they can drain out. Then of course, you've got accessories for shedding water. You seal your joints with tape. You have, other types of sealants such as silicones. And then of course, rain hoods above your hangers so that when water runs down, it can shed away from the penetration into the insulation. And then you have some mechanical systems that can be added to the pipe design that will help with water drainage. And you see in these slides, in these pictures that illustrate methods of separating the jacketing itself from the insulation or separating the insulation itself from the pipe so that it allows for any water that penetrated the system that gets to the pipe or water that has evaporated to the outer surface of the jacketing has a free flowing area to escape, possibly through drain holes. Like you see here, reduced time of wetness will lower corrosion. So in this illustration, you can see how water's got into the system. And then over here, you see the evaporation process of the water then migrating out to the outer jacketing surface. It'll condense against the cooler surface and of course, drain out through the drain holes. But with these collars that can often be engineered in, they keep the insulation away from the pipe itself. So the insulation then has sort of a way of being separated from the standing water as well, and also allows for gravity to pull it down the pipe towards a lower lying area for quicker exit. And then of course we get back to this idea of inspection and testing. So you can add into your system drains, inspection ports, and vents that allow you to, inspection ports to go and see what's happening under the insulation. Vents simply allow for opportunity for, as it states, venting, and then of course drains, drain. So these types of accessories are all part of the system that can be engineered in to help mitigate corrosion. So inspection and maintenance. In this final section, we'll introduce some resources owners can use for their inspection and maintenance procedures. So maintenance should follow a risk-based procedure. Knowing where to allocate resources will help maximize your maintenance budgets. So in this sense, these types of solutions are simply this, where you can run a probability versus consequence analysis where you can say, is the system high probability of corrosion? And if I take that and I say, if corrosion happens, what is the severity of the consequence? So if you have a high severity, high frequency of corrosion, and that if the pipe should burst, you can suffer some significant environmental damage, well, you would see right here, you would probably rate that a 9 and say, we need to focus on a maintenance inspection plan for that. And conversely, if it's in an area where it's very low chance of corrosion anyway, and the consequences are minimal, then you would say, I'm not going to allocate as much resources towards inspection and testing. Again, this all contributes to managing the cost of ownership and what's going to bring us the most successful way to getting there. And then you can also take this strategy a little further by using a chart like this. And this chart just simply draws connections, inner connections leading to the same outcome, meaning what is the highest chance of corrosion and the net consequences if we do not pay attention to it. Now, of course, this chart looks a lot more difficult than this chart as far as analysis go, but this particular chart factors in significantly more variables for you to consider. But either way, these methods are great tools to take into account and to solve the intricate problem of corrosion under insulation. And then finally, all this is a couple resources you can take a little further in the process. So the insulation industry, like all, is suffering from a dwindling knowledge base. And because, basically we have the older generation retiring and leaving the workforce, and I can't speak specifically for Peerless and their recruitment process, but I know within the insulation world, a lot of students aren't coming out of university looking for that first insulation job. So we have to do some things to make sure we reinforce the knowledge base within our industry. So NIA, the National Insulators Association, has put together a thermal insulation inspector certification course. There are also inspector programs in Europe like Frozio. The aim is to mimic the rigorous inspection standards of coatings and surface preparation. So if you're adding to your knowledge base, NIA has a couple courses to go for. And for those of you who do not know a program, so for those of you who don't even know a program like this exists, there are associations that are actively trying to advance the industry and bring up the level and quality of insulation, not just for manufacturers, but for distributors, installers too. And quite honestly, what Peerless is doing today is all part of increasing that knowledge base within our industries. It's constant learning, it's constant investigation into new things that are happening out there. How are other people solving the problem? What is our best way forward? So to wrap things up, we went through several reasons why it pays to insulate, not just in a financial sense, but also in an environmental and safety aspect. CUI is a system challenge that must be addressed and planned from design phase to decommissioning in order to minimize the overall cost effect. We also looked at tools for CUI mitigation that can extend the lifetime and provide longer maintenance-free periods, and thus it lowers the operational costs. And finally, the choice of insulation impacts the corrosion rates and overall costs, and careful consideration should be selected. So I'm hoping you found this presentation informative, and we were able at least to help you get to a starting point in reducing your total cost of ownership. We'd like you to thank everyone for joining us today, and thank Peerless for inviting us to bring more awareness to the industry. We're sticking around for a few more minutes to address some of your questions, and don't worry if we don't get to your question right away, we'll answer them for sure by email. So I'm going to send that back to you guys. Thank you.
Perfect. Thank you, Dave. Great job. I'm going to pass this back to Kevin real quick, but we do have a question still lingering out there that came in through the chat. And I will remind everyone else out there that if you do have something that you want to ask out loud, you should see an icon in your control panel that looks like a hand. And that's a way you can raise your hand, and then I will unmute you, and you can ask the question out loud for everyone, and for Dave or Jonathan to answer. But for now, Dave, we do have a question that came in, and the question is, so the belief is that calcium silicate is commonly used for stainless steel piping. Fiberglass is not recommended, potentially due to chlorides. Can you comment on the use of stone wool with stainless steel piping?
The answer is yes, I could comment on that. You know what? I would rather, that's a little bit of a different question for now. Can I take that one by email?
Yeah, absolutely.
Yeah, I would like to follow up properly on that with email.
Okay, perfect. Yeah, we'll let the person know that we'll follow up with that one separately.
Yes, thank you.
All right. No questions at the moment, and it doesn't look like any hands. Oh, I'm sorry, there is a hand raised. Chet, if you are able to, actually, it doesn't look like you are connected to audio. Oh, Oh, there we go. Looks like the question just came in via chat. Are there drainage or water management solutions for vessels?
They would be very much similar to that of a pipe. So yes, the answer to that is yes. So when it comes to vessels, depending on their orientation, of course, is where you would put the drainage holes. But for the most part, when you're looking at drainage system, you're talking about water shedding toward gravity for sure. And so that everything you do in relation to weatherproofing a vessel has to have in mind, where is the water going to go? So from top to bottom for sure, and where is the most likely points of entry, and wherever those points of entry, water has to have a way to go to a lower point. So is there mechanical things out there? That's beyond my scope. My suspicion is absolutely yes. There are mechanical devices for vessels. Who I could point you to at this time, I don't have an answer to that.
Okay, we'll see if there's any follow-up on that. Maybe follow-up outside the webinar. Just one more that came in quickly. All the testing that you did about water absorption, was that something that you guys did in-house, or did you have a third party perform that testing? And do you have, like, you know, a data set or results summary that you could potentially share?
Okay. Yeah, no, definitely. All our testing is third party. That's just simply to avoid the biased possibility or anything that could come into this to the results by way of bias. So yes, they're definitely third party, and yes, the results are definitely available. However, I would note that we only make the results of our installation available, because we can only truly say and testify to the results of our installation, not to imply the other installations are incorrect, but we just don't supply those results.
Okay, perfect. It doesn't look like there's any more questions at the moment, and we don't have any hands raised. So Kevin, maybe this is a good time for you.
Great. Thank you very much, Dave. Really, really appreciate your support today. Great job. Certainly a lot of information there, and seems like it absolutely is a trouble spot out there. So if you're looking at the screen, we mentioned a handout earlier, and this information is taken from that process manual. It is real in depth. If you haven't captured it yet from the handouts section of the control panel, you may want to grab it. Again, regardless of the type of installation you use, you'll find it definitely valuable. So thanks again. As far as next week goes, we do have quarter turn valves with J-flow controls. This will really be a deeper dive. Many of you may have been with us in week 1 of this initiative, where we did basically just a general overview of different valve types, gates, globes, checks, ball, butterfly. But this will be a really deep dive into ball, butterfly, and plug quarter turn valves. And it'll be a part 1 in a series. We'll eventually get into actuation with J-flow, and then finally control valves. So really looking forward to that. If you do want to see any of the past recordings, certainly they are on our website, including the Valves 101 that we just mentioned. The country, if you're wondering, if you guessed, the country is Pakistan. So congratulations to any of you who are geography wizards. I would have never gotten that. So once again, we appreciate your attendance. Thanks for joining us. The folks at Rockwool, great job. And you will be getting a survey, a 1-question survey to follow up this. And again, please do fill it out. This topic actually came as a result of a survey that we received. So we appreciate it. And also, if you follow us on LinkedIn, you'll be sure to not miss any announcements for future e-learning sessions. So we do have a LinkedIn page that we'd be happy to share it with you. So thanks again. Take care. And once again, stay safe, everybody. Talk to you next week.